we went through the transistor operations. Again, I know some of you did not take any circuit class before or transistor class before, but I know you guys are smart enough. But I do want you to just follow my slide. If you have any question, you must ask. For some of you, you already done that in E124, but still make sure that you understand all the important concepts because we're going to use this when we go to low temperature. Okay, so let me remind you one more time what happened. So this is a transistor, right? So we have three terminals. This is source, this is gate, this is drain, and this is NMOS because the source and drain are N-type. The substrate has to be P-type, right? P-type means that you have a lot of hole. Before we apply a gate voltage, you have NPN, right? Or back-to-back NP diode. It's not going to conduct. It is an off state, right? This is a first order analysis. And so we apply a gate voltage to it to invert the channel from accumulation mode to depletion mode and eventually to inversion mode. Inversion mode that means that originally I have a lot of a lot of hole, right, in the substrate because it is a P-type substrate. I apply a positive voltage so that eventually on top, at the bottom, it is still hole. But on top, the top surface, it becomes N-type, right? So I have a conductor. This is just like a conductor. Electron, electron, electron. Make sense? Any questions? But what's so special conductor? We have a lot of resistor like that. The important thing is that the conductivity, how good it can conduct the electrons, depends on the gate voltage. And that is what make it a so-called active device, that you can have power gain. You use a third terminal to control the current through here. And you know this concept very well, just like the switch on the wall in this classroom. I just need to apply a very tiny force to turn on the circuit, and I can conduct a lot of electricity, a lot of current through this building, right? This current can be large enough to power a Tesla or to power whatever, right? I only apply a very tiny force. That is like an amplification, right? So we've gone through that already. But in this slide, what we did in the last lecture was that. Now, I have 0 at the source. Gate voltage is 2 volt, and the threshold voltage is 1 volt. What is threshold voltage again? Yeah, just tell me what that, yeah. No need to be polite, say it at the same time, okay? Yeah, the voltage you need to turn on the transistor, right? Is the gate voltage after which you form the inversion layer. So since I'm at 2 volt and threshold voltage is 1 volt, of course I turned it on already, right? Now the question is, on the drain, I start with 0.5 volt. What will happen? So last time we said that we already learned that the charge across the capacitor Q equals to C times V. So in this case, E equal to the oxide capacitance, right? Times the gate voltage minus the substrate potential. And then we will also minus the threshold voltage because we only care about the mobile electron. We don't care about the depletion charge, which is immobile, right? Because when the difference is just equal to VTH, then you just able to invert it. There's no electron. You just turn it off. Okay? Now, so that's why I put here the charge at this point is COS times 2 minus 0 minus 1. You give me COS. But here I have 0.5 connected to the drain. So at this point it's 2 minus 0.5 minus 1, which is 0.5 COS. So the message here is that I have more electron on the left than on the right. It's not symmetric anymore, which makes sense because the voltage you apply to the source and the drain are not symmetric. They are different. And then we say, what if I continue to increase the drain voltage? For example, I increase from 0.5 to 1 volt. Then the charge on the right is going to be Cox times 2G, this is Vg, minus 1, which is the potential here, 1 volt, minus 1, which is the threshold voltage. I get no inversion charge. So the thickness that is drawn here represents how much charge you have. On the left, I have quite a lot of electron. On the right, I just have no electron. And this is called pinch off. It's just like you pinch off something. You pinch the tube, right? Any questions? Now, if no question, then if I keep increasing VD, right? For example, in this case, the VD is larger than 1 volt. Then what will happen? This pinch off region will shift to the left because here, for example, let's say this is 1.5 volt. Then this point is also 1.5 volt. But then it will gradually drop until this point, which is 1 volt. And at this point, you just pinch off because, again, based on the equation we have learned, this point is Cox times 2 minus 1 minus 1, right? Because it's Vg, which is 2, minus, at this point, is just 1 volt, and then minus the threshold voltage. When you go over here, of course, you don't get negative or means the whole here, because this is a simplified model. But in summary is that when you keep increasing the drain voltage, this pinch-off region will be larger and larger. Okay? And that's why we define a quantity called Vset, which is Vg minus Vth. Okay. Any question about this pinch-off? Yeah.
What exactly are we pitching about?
What exactly are we pinching off? Very good question. Now, if this is 0 volt, I have a continuous layer of electron, right?
Mobile or remote?
Mobile, yeah. Yeah, because inversion, I have the electron. Before inversion is depletion, but they are not electron. They are negative charge, but they are fixed ion. So now I have a continuous layer of electron when this is 0 volt. And then what do we mean by pinch off is that when you increase the VD, the electron here becomes less and less. Eventually, you don't have mobile electron, but you have depletion charge. You are right. I have lots of depletion charge, which is immobile. So this pinch off is just like you have a water hose. Now I squeeze it, I pinch it, so that you don't have water in that region. Something like that, the idea. Yeah. No, the depletion charge, so it's good to review this one more time. How do we dope a silicon, right? A simplified view, if you have learned that before. You have a silicon lattice. These are the atoms. Right, you have a lot of silicon atom. Is this okay? Are you okay with this picture? So how do we dope it? Of course, this is a simplified view. What we do is for example, we replace this silicon by a boron. Okay, the boron, again, you only have 3 electrons on the outer shell. Silicon have 4 electrons on the outer shell. Then you can because this is a little bit confusing if you're not familiar with this, but you can consider this as a negative charge boron plus a hole. Hole is the carrier in the p-type because you have 3 electrons, right? But then you just assume that I borrow 1 electron, then you have 4 electrons, you can complete this bonding. But then you create a hole somewhere. And this is the hole that is moving, right? We don't go to solid state physics, just think in this way. Or opposite, if it's n-type, I put an arsenate, you have 5 electrons. then I have one electron that can leave the arsenic, and then arsenic becomes positive charge. Here, boron becomes negative charge. So depletion is talking about I remove away this hole, then now I have a negative fixed charge in that region. Make sense? Yeah.
Then, as far as current through the base source
Yeah.
in the pinch-off region, that we don't have any, right? The COX is 0.
You mean you don't have any current because of pinch off? Is that what I say? No. So this is something we need to further clarify because you asked. Otherwise, we will skip because it's too confusing. Firstly, this is just an approximated model. So it is not really that you don't have any electron here. It's just that very, very low. And then how do we understand this without really solving the full Poisson equation? You can think this as a waterfall. It is a region you have a very high electric field. So think about this waterfall. This is the river, and then you run into the cliff. When pinch off is talking about this region, it's like the cliff, delta L. So yes, you can say that here the water is, I have a lot of water here, so it just flows slowly. But once the water reach here, they just run very fast. So you can say, okay, at the waterfall, you barely have any water, right? Barely have any electron. But because of the continuity, you do run very fast. Whatever comes in, run very fast. So whatever, here you have a slower electrons, but here you have faster electrons. So overall, you do have a current going through. So you can think in this way. Yeah, so again, very good question. Pinch off is just a simplified model, but it's a good way to think about that. But when you reach the point saying that now you don't have electron, how can you have current? Then we need to go back to a reality picture. You do have some electron, and they travel at the highest speed that they can have in this pinch off region.
But does the formula I forget if that only holds for the saturation region, like WNL, COX, that is still hold for this?
Yes. Yeah. So you mean this equation? Charge equation? The current, right?
Yeah,
Yes, that's what I want to say next. Then how should we derive this current? So I will discuss this in the next slide. Do you have other questions regarding this?
So the thing
It does. Yes, it does. Okay. Now, then let's go to this region, right?